It is I, Arthur, King of the Britons, and I'm here to deliver Josh Price's lecture today. All right, that's enough of that. Sorry. Welcome to today's lecture. This one's intended for Wednesday, March 20, whatever it'll be, 25th. Okay. I remember Wednesday, March 25th, because that was the day in 1998 that I opened my mission call. I don't know why I always remember that. But in any case, we're going to pick up where we left off last time. Today we'll talk about the structures and the features of the remaining amino acid side chains. And then after that, we'll go on to talk about some interesting relationships between sequence and structure within peptides and proteins. We'll talk about a class of proteins and peptides called the alpha helical coil coils, and these are among the best understood protein structures in nature, and chemists and biologists have really got a feel now for the rules that link the sequence of a peptide to structure and then function. So with that, let's take a look at Notability, and I'll just remind you of where we were last time. We had discussed the series of nonpolar amino acids, including alanine, valine, leucine, isoleucine, and methionine, and we had looked at their Ramachandran plots and found that they each fit fairly well within the alpha helical area as well as the beta strand area. We also talked about phenylalanine and tyrosine, and these are the aromatic amino acids. And tyrosine is interesting because not only does it have a benzene ring, but it also has an OH group whose pKa is about 10, and so there are some cases in which that proton can be removed and the OH or the oxygen act as a nucleophile. We also talked about the fact that with aromatic rings, because of the difference in electronegativity between an sp2 hybridized carbon and a proton, the edge of the aromatic ring is electron poor, whereas the face is electron rich. And that will have some interesting implications in protein structure later on. And then finally, we talked about the amino acid tryptophan, wheel hunting wabbits. Elmer Fudd's favorite amino acid, tryptophan with W. It has an interesting aromatic side chain called an indole, where you have a 5-membered ring with a double bond and a nitrogen fused to a benzene ring. The indole NH is a good hydrogen bond donor, but it is not acidic and its pKa is quite high. Lone pairs on the nitrogen are involved in resonance with the double bonds nearby, involved in the aromatic pi system, and so are not available for acting as nucleophiles or acting as bases. And tryptophan is comfortable in the alpha and beta regions of our Ramachandran plot. Now, the next amino acid is unusual because it seems like it could fit fairly well in a couple of different categories. This amino acid is called histidine, and its 1-letter code is H, and the 3-letter code is HIS. Histidine shows a little bit more interesting preferences in the Ramachandran plot. Again, fairly comfortable in the alpha helical region and in the beta region, but you also have this interesting region there. And then you also have here, which is probably the left-handed alpha helical dihedral angles. And we won't worry about what that particular maximum that I was thinking about labeling is. All right. So histidine, let's see, we'll draw our little squiggly line. Here is the alpha carbon. Here is the side chain beta carbon. Here is the gamma carbon, and there's a 5-membered ring containing 2 nitrogens. And that histidine can exist in 2 possible protonation states of physiological pH. So you have this one, which is its neutral state, and maybe we'll shrink that a bit. Maybe we'll shrink that. Shrink that a bit. It doesn't want to shrink, guys. Fine. And it's in well, that one shrunk. The other day, my son Nathan made the observation that the past tense of the word shake is shook, as in the earthquake really shook the house. And so he wondered, if shake's past tense is shook, then shouldn't the past tense of quake be quook? The earth quook all over the place? Not sure. All right. The histidine side chain can exist in 2 different protonation states. The pKa of this imidazolium ion is 6. And of course, its conjugate base is called an imidazole side chain. You'll notice that the imidazole and the imidazolium are both aromatic. So histidine does fit into this aromatic character. But the fact that under physiological pH, that is at about pH 7, you're going to have about 10% imidazolium form positively charged and about 90% neutral, means that histidine sort of fits in category with the aromatic amino acids, but also fits in the category with the cationic amino acids. So it's somewhere in between the aromatic amino acids and the cationic amino acids. Histidine is found in a lot of active sites of proteins, particularly proteases and lipases. Next comes lysine. LYS is the 3-letter code, 1-letter abbreviation K. You may not be used to that now, but if you give yourself a little bit of practice, you'll make that association fairly completely. Very comfortable in the alpha area of the Ramachandran plot, in the beta area, even in this polyproline type 2 helix area, and a little bit, not a huge amount, but a little bit in the left-handed alpha helix area. The lysine side chain has a number of CH2 groups, and then at the end of this long hydrocarbon chain, it has a nitrogen. So here is the alpha carbon, here is the beta carbon, and with lysine you go alpha, beta, gamma, delta, epsilon, and then on the epsilon carbon you put the ammonium group. And of course, the ammonium group is in equilibrium with its conjugate base, simply just the amino group. Oops, alpha, beta, gamma, delta, epsilon. And the pKa for lysine is, dang, I thought I remembered it. Let me look it up real quick. Sorry about that, folks. I want to say it's around 9, but I want to make sure I'm not leading you astray. Dun, 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 dun. All right, we're finding it lysine, pKa of the side chain. Oh, sorry, it's around 11. All right, which means at physiological pH, basically you're going to have greater than 99% in the positively charged form, with much less than 1% in the neutral form. That being said, even though most of the lysines are positively charged, they can act as nucleophiles under certain situations, which we can talk about. But right now, the most important thing is that you think of lysine as being a positively charged amino acid. Next on our list is arginine. Its one-letter code is R, which sort of makes sense. Three-letter code ARG. And it is the pirate's favorite amino acid. I'm waiting for you to have plenty of time to chuckle at that. Arginine is kind of like lysine, only its side chain is not quite as long. With arginine, you go alpha, beta, gamma, delta, and then on the delta carbon, you put an NH, and then attached to that NH, you put the following functional group. This functional group is called guanidinium, and it has a pKa of 12, and it would be in equilibrium with its conjugate base. And to draw the conjugate base, you just draw the same functional group, but you remove a proton. Now the functional group is called guanidine. Should point out that at physiological pH, you're going to have greater than 99% in the positively charged guanidinium state, and much less than 1% in the neutral guanidine state. Also should point out that that positive charge is delocalized on all three of those nitrogens, and that the guanidine functional group is planar because the central carbon there is sp2 hybridized. Notice that arginine is very comfortable in the alpha helix and beta sheet areas. And that completes our journey through the positively charged amino acids. So we'll give them the color blue for reasons unknown to me or you. We'll just choose the color blue, and then we'll color it in. But we'll remind ourselves that histidine is aromatic. There's a question on your practice exam about which nitrogen gets protonated in histidine, and the answer to that has to do with aromaticity. It's a question you've seen before, probably in chapter 17 on aromaticity, but it may be worth some review. Now we'll get, oh, I guess I should fill in, these are the cationic amino acids. Now we'll get to the negatively charged amino acids. We'll call this first one aspartic acid or aspartate. Aspartate is what you would call the conjugate base form. Its one-letter code is D, and you're going to have to just memorize that. There's no rhyme or reason for that because we've already used the letter A for something, and we're going to use the letters S and P for other things, and letter T for other things. So poor aspartate just ended up with D. The conjugate acid of aspartate is aspartic acid. You go alpha carbon to beta carbon to gamma carbon, and the gamma carbon is a carbonyl carbon with an OH on it. So that's aspartic acid. And of course, aspartic acid, the side chain proton, the carboxylic acid proton has a pKa around 4, meaning that under physiological conditions, you would expect most of the aspartic acid to be in its conjugate base form, which would be negatively charged, gamma. Okay. Aspartic acid is interesting because you can see that it has a slightly different preference for dihedral angles than do most of the other amino acids. It certainly has a decent preference in the alpha helical area, but a very strong presence in the left-handed alpha helical area, and not so much of a presence in the beta strand type area. We won't worry about what these other maxima are. It'll be enough for you to just remember that aspartate's just a little bit weird in terms of its conformational preferences. Aspartate is found in a lot of enzyme active sites. Along with histidine, it's part of the catalytic triad that makes serine proteases and lipases work. The next amino acid is called glutamate. One-letter code E. And its three-letter code is GLU. Glutamate is one methylene group longer, one word for than aspartate. One word for being one methylene group longer in organic chemistry is being a homolog. So glutamate is the homolog of aspartate. Here is its conjugate acid. pKa is also around 4. So at physiological pH, you'd expect greater than 99% to be in this sort of conjugate base form. That's negatively charged. Glutamate is comfortable in alpha and alpha helical and beta strand situations. And these amino acids comprise our anionic amino acids. That is, at physiological pH, these amino acids are negatively charged. That's going to be important because we're going to see that one of the major ways in which side chains within proteins can interact with each other is via ion-ion interactions. A positively charged lysine, for example, interacting with a negatively charged glutamate. And sometimes they call those salt bridges. So these are the anionic amino acids. Now the rest, we still have, let's see, 1, 2, 3, 4, 5, 6, 7 to get through. The rest are going to be the polar amino acids that are neutral, and then 2 last sort of weird amino acids. All right, the next amino acid is serine. 1-letter code is S, 3-letter code is SER. Serine is a simple amino acid side chain. Here you have the alpha carbon, the beta carbon, and then on the beta carbon an OH group. As you might expect, the pKa of that side chain is about the same as the pKa of an alcohol or water. So it's mostly going to be in its fully protonated form at physiological pH, though sometimes serine can act as a nucleophile. Here it's fairly comfortable in both alpha and beta strand contexts. It is polar but not charged, though you will see serine, as I said, act as a nucleophile in the active sites of some enzymes, particularly the serine proteases and lipases. Related to serine is the next amino acid, threonine, 1-letter code T. Threonine is like serine, only its side chain has a methyl group on it instead of a methyl group on the beta carbon in addition to the OH group. So here's the alpha carbon, here's the beta carbon, here's the OH group, and then on the beta carbon you have a methyl group. That beta carbon is a stereocenter. Threonine, like valine and isoleucine, is a beta-branched amino acid. Like serine, it should have a pKa around 16, so mostly in its fully protonated state, comfortable in the alpha and in the beta strand regions. And you'll note that all of the beta-branched amino acids are particularly comfortable in the beta region of the Ramachandran plot. Here's valine, and then here's isoleucine, and then finally threonine, all fairly comfortable in that beta region. Next is the amino acid cysteine, 3-letter code CYS, 1-letter code C. Cysteine is like serine in that it just has a beta carbon, but instead, as its side chain, but instead of an OH group, you have a thiol group, an SH group. The thiol sulfur atom, due to its size, is highly nucleophilic. So cysteine is the most nucleophilic of the amino acids, and you can target it selectively. It is in the active sites of cysteine proteases, as an example. It's also oxidizable, kind of like methionine, but instead of forming a sulfoxide, when cysteine oxidizes, it forms a disulfide. And a disulfide is where 2 different cysteine side chains are linked to each other through their sulfur atoms. So this is a disulfide bond, and this disulfide bond is used for structural stability in excreted proteins. It turns out that inside the cell is a reducing environment, and so cysteines in proteins inside the cell are in the reduced thiol form, whereas many cysteines outside the cell are in the oxidized disulfide form. Cysteine's comfortable in alpha helices, and its distribution in this upper quadrant of the Ramachandran plot is a little bit unique, and we won't talk too much about that. Next amino acid is asparagine. So named because I think of a connection to asparagus, but not really sure. The 3-letter code is ASN. The 1-letter code is N. Asparagine, so I guess that makes sense. Asparagine, if you look at its Ramachandran plot and then look at the similar plot for aspartate, you can see some similarities. Both have this strong maximum in the alpha helical region, and then another maximum at the where the x-axis intersects the plot. Same thing up here. They both have a strong maximum in the left-handed alpha helical region, and then they both have sort of a unique distribution of preferred values that don't necessarily align with being in a beta strand. Asparagine is just like aspartic acid, only instead of having a carboxylic acid at the gamma carbon, you're going to have an amide. The side chain pKa is high enough that we don't worry about it. It's always protonated at physiological pH. Asparagine is one of the amino acids that can be modified with sugars. It gets glycosylated. It can also participate in hydrogen bonding. Glutamine, like asparagine, is the amide version of glutamic acid. Its 1-letter code is Q, which makes no sense, and you just have to memorize it. But its structure will be exactly the same as the glutamic acid side chain, except the delta carbon will be an amide instead of a carboxylic acid. And those are our polar but neutral amino acids. I guess I should have said with cysteine that the thiol has a pKa around 8, so it can exist at physiological pH in its thiolate form, negatively charged thiolate form. But what color will we pick for neutral? Yellow seems kind of okay, so serine, and then threonine, cysteine, asparagine, and glutamine are in the neutral category of amino acids. They are polar but neutral. So we'll color them this yellow color. Struggling to stay inside the lines. All right, I'll just write down. Oh, that's not going to work. Let's choose a different color. Polar but neutral. And then these last few amino acids are in a category sort of all by themselves because they are weird. So you wouldn't necessarily think so just by looking at their structures. Glycine, for example, 1-letter code G, 3-letter code GLY, is the simplest amino acid in that here's what it would look like if it were involved in a peptide. It has no side chain. The alpha carbon is unsubstituted. There are just protons there. And because of that, glycine is the most flexible amino acid. And you can see this reflected in the fact that it is equally happy in right-handed and left-handed alpha helical contexts. And you'll see that basically everything on the left side of the Ramachandran plot is a reflection of what's on the right side of the Ramachandran plot. So glycine can adopt dihedral angles that most of the other amino acids can't, and that's because it's got no large bulky side chain. Next is proline. Proline is also a neutral amino acid, but unlike any of the other amino acids, proline has a secondary amine and is also cyclic. By the way, the one-letter code is P, and the three-letter code is PRO. Let me draw for you the structure of the proline side chain. Here is the nitrogen. It would be bonded to something else. When it's involved in a peptide, the nitrogen doesn't have a hydrogen on it. The nitrogen instead participates in this five-membered ring. A five-membered ring with a nitrogen in it is called a pyrrolidine, which isn't necessarily important. The fact that this amino acid is cyclic, the delta carbon is tied back on the amide nitrogen, restricts the available phi-psi values. So you can see that proline can adopt some phi-psi values that are consistent with the right-handed alpha helix and some that are consistent with polyproline helices. Interestingly, proline, because it can't hydrogen bond, even though it adopts dihedral angles that are consistent with helical formation, it's a helix breaker because its nitrogen can't participate in hydrogen bonding. It's found often at the end or at the beginning of a helical stretch of amino acids. So I don't know what we'll necessarily call these. We'll maybe highlight them in pink and just say these are our amino acids with strange conformational preferences. We saw with glycine that it was really flexible, whereas proline can only adopt certain phi-psi angles because of its restricted, because of its ring. Proline is an example of something we call pre-organization in chemical biology, which means when you make something cyclic, you can constrain it to only have certain shapes. So we will just call these the weird amino acids. And that is our tour through the family of the 20 proteinogenic amino acids. All right, now that we've talked about amino acids, we want to start talking about peptides, which are polymers of amino acids. And we've already discussed a little bit about peptide structure, but we need to introduce some important conventions. So let me draw a short dipeptide. We'll have, there we go. Oops. And let's say this one will be alanine, and this one, except that's the wrong stereochemistry. My apologies, friends. And this one will be valine. Okay. Couple of features of peptides. Notice that peptides have directionality. That is, the sequence of alanine and valine is different from the sequence of valine followed by alanine. Notice to the left, alanine is closest to the ammonium group, and valine is closest to the carboxylate group, whereas on the right, valine is closest to the ammonium group and alanine is closest to the carboxylate group. So we'll call this peptide directionality, and we will say that peptides have two different ends. They have an end where there is an ammonium group. We'll call this the N terminus. And then we have an end that has the carboxylate group on it. And we'll call this a C terminus. And it will be important to keep these two features distinct in your minds. And the distinction between these two ends helps you to see how the peptide on the left is different from the peptide on the right. On the left, the N-terminal amino acid is valine, whereas is alanine, whereas the C-terminal amino acid is valine. In contrast, on the right, the N-terminal amino acid is valine and the C-terminal amino acid is alanine. This is important because when we name these peptides, we're going to write their sequences always, and probably three more alwayses, from N to C. In other words, the proper name for the peptide here on the left is, in three-letter code, ALA and then val for valine, or one-letter code, you could just say the dipeptide AV. We'll call this a dipeptide because it has two amino acids in it. In contrast, the peptide here on the right, we would name VAL, ALA, or VA. And the important thing we're showing here is that the AV sequence is not the same as the VA sequence. Those are two different molecules. Let me say that again. The AV sequence is not the same thing as the VA sequence. Those are two different molecules. They might have two different chemical and physical properties. Pause there if that's confusing for you and re-listen to that section of the lecture until you can easily see the difference between dipeptides AV and VA. Okay, now that you've paused and we're back, let's talk about how we might write longer sequences of amino acids. And we'll call this primary structure of peptides, or rather sequence. And this is the order of amino acids from N to C. And this order of amino acids is the thing that determines the structure and ultimately the function of a peptide. So I'm going to write down the sequence of a peptide, and then we'll start to talk about the features of this sequence, and that will allow us to talk about the relationship between sequence and structure and function in the context of the alpha helical coils. So the sequence I'm going to write is derived from a yeast transcription factor called GCN4. RMKQLEDKN. Oops. EDK VEELSK NYHL ENE VARLKKL VGER. All right. When we write out the sequence this way, what we mean is that this arginine is the N-terminal amino acid, whereas this arginine is the C-terminal amino acid. And so we would need to understand, looking at that sequence, that if we wrote the sequence that way, we would be communicating that the N-terminal amino acid would look like this: alpha, beta, gamma, delta, and we'll draw the side chain as it would appear at physiological pH. Similarly, we would need to understand that the C-terminus, the C-terminal amino acid, would look like this: carboxylate at the C-terminus, alpha, beta, gamma, delta, then nitrogen, and that would be a positively charged amino acid at physiological pH. Okay, so if you need to, go back and review the structures and one-letter codes for the amino acids until it's very clear to you what each of the side chains is. So let's note some of the features of this peptide by first highlighting the side chains that would be positively charged at physiological pH. So we've already said the arginines would be positively charged at physiological pH. Another positively charged residue is lysine. Remember, lysine would look like this: alpha, beta, gamma, delta, epsilon. Okay, so all the K amino acids, or lysine amino acids, are going to be positively charged at physiological pH. Oh, there's another arginine, and there are two lysines. So overall, 1, 2, 3, 4, 5, 6, 7, 8. I have 7 positively charged amino acids. Let's look for the negatively charged amino acids. Remember that glutamic acid is one of these. Glutamic acid in the peptide would look like this: alpha, beta, gamma, delta, with the carboxylate on the delta carbon. And so every time we see an E, that would be a negative charge. Aspartic acid is 1 methylene unit shorter than glutamic acid, so every time we see a D, that's a negative charge as well. So let's read through the sequence. And actually, we want to make it easier to tell. So let's draw the negative charges under. Here's an E, there's a D, another 2 E's, couple more E's, and one final E. So 1, 2, 3, 4, 5, 6, 7. Hold on here. So let's count how many positively charged amino acids we have. 1, 2, 3, 4, 5, 6, 7, 8. Got that wrong. 8 positively charged amino acids. And then 1, 2, 3, 4, 5, 6, 7 negatively charged amino acids. And then, of course, we would add the positively charged N-terminus and negatively charged C-terminus. So overall, we would have 9 positive charges offset by 8 negative charges. The net overall charge on this peptide would be +1. Okay? And we might expect that as this peptide adopted a regular structure, it might also allow some of these positively charged amino acids to interact with negatively charged amino acids. But one of the other features that we can see as we look at this peptide sequence is that there are several nonpolar amino acids in this molecule. So I'm going to highlight the nonpolar amino acids in orange. And here is one. It's methionine. And I'm noticing that if I count 7 amino acids from methionine, 1, 2, 3, 4, 5, 6, 7, I have another nonpolar residue. I will use the term residue interchangeably with amino acid. A residue is what you call an amino acid within a peptide. Strange terminology, but it's hard for me to break because I've been in the peptide world for such a long time. So if you hear me say residue, I just mean amino acid in a peptide. If we count 7 residues or amino acids from valine, 1, 2, 3, 4, 5, 6, 7. We have another amino acid. It's in this case, it's polar. But if we count 7 amino acids from there, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, you get another nonpolar amino acid. And then 1, 2, 3, 4, 5, 6, 7, you get another nonpolar amino acid. So one of the things we're noting about this sequence is every 7 residues, in general, we have a pattern of nonpolar amino acids. But if you look at the sequence, there's another group of nonpolar amino acids that we haven't accounted for. If we look at the methionine, 1, 2, 3, 4, you've got a nonpolar residue there. All right, let's see if we count 7 amino acids from this pink lysine, the L amino acid, 1, 2, 3, 4, 5, 6, 7. Oh, look, there's another lysine. Let's count another 7 from there. 1, 2, 3, 4, 5, whoa. 1, 2, 3, 4, 5, 6. You know what, folks? I think... Oh, I missed an amino acid in this sequence. There is another L between all right. There's another L there. I missed that sequence where I was copying it down, so forgive me there. 1, 2, 3, 4, 5, 6, 7. There's another leucine. Then 1, 2, 3, 4, 5, 6, 7. There's another leucine. 1, 2, 3, 4, 5, 6, 7. There's another leucine. And you may have noticed there were a couple of other nonpolar leucine residues at other positions, but overall we're seeing two sets of repeating nonpolar residues. So you've got the orange set, and then you've got the pink set, where every 7 residues from the pink you have a pattern of nonpolar amino acids. And the two patterns are offset from each other. The methionine, the space between the methionine and the leucine is 3 amino acids, and then the space between the leucine and the valine is 4 amino acids. And so we might continue this pattern of 3 and then 4, 3, and then 4, 3, and then 4. This regular repeating pattern of nonpolar amino acids is going to be important for the structure of this peptide. And in fact, peptides and proteins with this pattern of nonpolar amino acids that repeats every 7 residues are typical of the peptides. I'm sorry, not explaining things very well, and I apologize. This sequences that have this characteristic 7 amino acid repeating pattern of nonpolar residues, actually 2 7 amino acid repeating pattern of nonpolar residues offset from each other by 3 or 4 amino acids, is characteristic of a class of protein structures called coiled coils. And because this involves a repeating pattern of 7 residues, we will often call this sequence pattern a heptad repeat. And for clarity, I'm going to recopy this sequence, and I'll show you the heptad repeat. If it's okay, I'm going to get rid of the charge things. Okay, and maybe for clarity, I will number the amino acids starting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. And we can give each amino acid within this heptad repeat a designation for its position, A, B, C, D, E, F, G, and we will see that nonpolar amino acids go at the A position and at the D position. So here's your heptad repeat, A, B, should choose a different color for clarity maybe. Let's go blue. A, B, C, D, E, F, G. Oh, we lost the circle on methionine. That was depointing. Depointing, that's not a real word. That's a word that my son Nathan made up years ago when we lived in Madison, Wisconsin while I was going to grad school. And we had gone to the church for a Pioneer Day broadcast, and Nathan was like 3. And I think we had probably told him it was going to be great because we were going to be able to hear the prophet speak. Well, we got out of this meeting and Nathan says, well, that was depointing, by which he meant disappointing. And we've laughed about that ever since, and that is now our new word for disappointing circumstances. All right, well, you can see that within this 7 residue sequence, residues A and D have nonpolar amino acids, and we'll follow that through in each of these sequences. I'm sorry, in each of these series, in each of these heptads. In general, you see a nonpolar residue at A and again at D. We'll put an asterisk here and come back to this as to why there is a polar amino acid at an A position here. But in general, you've got this sequence pattern, A, D, and there's an exception here. This is at the end of the peptide, and it turns out it won't matter for the sequence that we're looking at. All right. So what might you expect this sequence to do? You need to know something about nonpolar amino acids and what's called the hydrophobic effect. Long ago in 351, we talked about why oil and water don't mix. And if you have a beaker here, and those of you that have taken the organic lab know this, suppose we have water here and then some hydrocarbon, let's say hexane here. You can shake up the water and the hexane, but they always separate out to these 2 separate layers. They are not miscible, is the word that we're looking for. Why aren't they miscible? What would be wrong with having a hexane hydrocarbon chain in this surrounded by H2O molecules? It must be that having them separate is lower in energy than having them together. And let's see why that might be. So hexane is a liquid, and you can imagine individual hexane molecules. The way they would interact with each other would be through weak van der Waals interactions, transient polarization of their electron density, not permanent, but in 1 second there may be an aligning of partial positive charge along one side of the molecule and partial negative charge on the other, and this would fluctuate, but these would be the intramolecular forces that would tend to hold the hexane molecules together. In water, you would have hydrogen bonding in addition to these van der Waals interactions. That is, one water molecule can hydrogen bond with another. With another, and so on. And because both of these phases, the organic or hexane phase and the aqueous phase, because they're both liquids, you know that these interactions are short-lived and flexible and fluctuating. That is, the water molecules don't exist in a rigid cage of hydrogen bonding, but they trade rapidly who's hydrogen bonding to whom. Now let's consider the case. So this is what the two would look like when separate. Now let's consider the case where a molecule of hexane might be dissolved in water. So here's your molecule of hexane. It can still participate in van der Waals interactions, but it cannot participate in hydrogen bonding with water. The water molecules have to surround hexane, but they can't hydrogen bond with it. And the lack of their inability to hydrogen bond with hexanes, with the hexane molecule or the nonpolar molecule, makes it even more important for each water molecule to hydrogen bond with another water molecule. And those hydrogen bonds become stronger and more rigid. Stronger and more rigid, you say? Certainly that would be good, right? Because strength of bonds formed versus bonds broken, strength of interactions formed versus broken can often be a measure for how favorable some process is. But remember that there's another thing at play here. Not only in chemistry, you have to consider not only the strength of interactions formed versus broken, but you have to, which is more an issue of enthalpy, but you also have to consider change in order versus disorder. Okay, so when the two phases are separate, each individual phase is fairly disordered. However, if you dissolve hexane in water, you get a rigid network, or maybe even an ice-like cage of slow-moving water molecules that surround the hexane. And this is a very ordered state. So going from separate to dissolved has a high delta G. Delta G is positive, meaning that going from dissolved to separate is energetically favored. And the reason is when you go back from this dissolved state to the separate state, you release these water molecules that were in this rigid cage around the hydrocarbon back to being disordered and fluctuating in the solvent. So you've got the separate state and in equilibrium with the dissolved state, and the equilibrium constant favors the separate state because of entropy. We call this the hydrophobic effect. And again, it is entropy driven because when you go from dissolved to separate, when you remove the nonpolar molecule from being exposed to water, you increase the entropy of the system. In contrast, if you go from separate to dissolved, you decrease the entropy of the system. Now, how might this apply to peptides and proteins? Well, we need another page. How might this apply to peptides and proteins? Well, a peptide sequence, which I'm just going to draw as an unfolded squiggly line, might have lots of nonpolar residues or nonpolar amino acids in it. Here's an isoleucine. Here is a phenylalanine. Here is a leucine, and so on. And it might have also lots of charged amino acids. We won't draw them, but there might be positive charges and negative charges. And in the unfolded state or conformation, you would have a rigid network of water molecules surrounding the nonpolar side chains. And I'm going to indicate this with this solid blue line surrounding each of the nonpolar amino acids. The charged amino acids can interact with water just fine and participate in the regular sort of disordered network of hydrogen bonding that's present in water. But these, and we'll have interspersed red lines here to indicate the strong and rigid hydrogen bonds that the water molecules are making with each other as they surround the nonpolar amino acid in the unfolded state. But if the peptide adopts a folded conformation, let's suppose it folds such that the nonpolar amino acids are grouped together in the interior of the protein. Oops. Let's just imagine the nonpolar amino acids are grouped together in the interior of the protein. All of a sudden, and you would continue to put the charged amino acids on the surface because they can interact in the transient and disordered network of water molecules via hydrogen bonding. But if we sequester or bury the nonpolar amino acids from solvent, what that does is it releases all of these water molecules that used to be surrounding the nonpolar amino acids to bulk solvent. And you have many H2O molecules that are free to participate in the disordered network of hydrogen bonding that's present in what we will call bulk water. So this process of folding or burying non-polar amino acid residues allows water that would otherwise have surrounded the nonpolar residues in a rigid network to be released to the more flexible network of water molecules in the bulk solvent. And this process of folding is favorable. Delta G is negative, equilibrium constant is greater than 1, and it is driven in general by the hydrophobic effect. So that's about enough to be going on with. I had intended to have only 4 lectures on peptides and proteins, but we may need 5. So this completes, I think, the 3rd lecture on peptides and proteins. We'll have part 4 next time, part 5 after that, and that should conclude the material for exam 3. In the meantime, stay safe, stay socially distanced. Hope everything is well. Be good. I love you. Things are going to turn out okay. And we'll see you next time.